Welcome to NPTEL lecture series, a basic course on electric and magnetic circuits. We are now in module 3 dealing with DC transients. So, transients otherwise called also switching transients. So, this module is associated with resistance and inductance switching on, resistance and capacitance switching on, capacitance charging, capacitance discharging, and so on. However, before that we will learn the basic properties of capacitance and inductance, series parallel combination and like that, and then we proceed for the switching transients. In these switching transients, we will only confine to RL and RC type. So, let us move to the first lecture. This is on capacitor. So, we will learn about the properties of capacitor, basic equation, and then series parallel combination of capacitors, and also the star delta conversion associated with capacitor combination. So, we know earlier also in the AC circuits analysis, the capacitor, its property from the capacitance by which its two parallel plates, if we apply voltage across them, then they have the capability to store charge. That capability is measured in terms of capacitance, and the device is called capacitor. So, the more it can store charge for a given voltage, then the capacitance is higher. This capacitance is measured, its unit is farad. Farad is very large value. So, typically available capacitors are measured in terms of, or unit we provide in terms of microfarad. We know that a capacitor is symbolically represented in terms of two parallel plates, inside which a dielectric material may be there. So, the capacitor having a capacitance C, if a current flowing into the capacitor is I, and we have the corresponding polarity of voltage as designated as shown here V, then the basic relation for capacitor is Q equals to C V, where Q is the charge stored in the capacitor parallel plates, plus Q left side, minus Q right side in this case. Then the rate of change of charge is current flowing into the capacitor, that I equals to dq upon dt, and that equals to C dV by dt. The current through the capacitor is C dV upon dt, where small v is the voltage across the two plates of the capacitor. So, this relation reveals about all the properties of the capacitor, voltage current relation. So, if you see here this dV by dt, that the V cannot change abruptly. So, that means that dV with the dt tends to 0 and the dV having certain value, then the dV by dt tends to infinity. So, that is practically not feasible. So, if that is so, then the corresponding current has to be also, current also tends to infinity. So, therefore, we say that from this relation that capacitor voltage cannot change abruptly. That implies that this kind of voltage cannot happen for a capacitor. So, the Vc or the voltage across the capacitor cannot happen like this, because if that so, then the corresponding current has to be infinity, which is not practically possible. So, however, if you say that the corresponding voltage varies like this, can voltage across the capacitor can vary like this. So, if there is a variation like this, then we have a dV by dt is limitation. So, current is limited, and when the corresponding voltage is fixed, dV by dt becomes 0. So, the corresponding current becomes 0. So, that the voltage across capacitor cannot change abruptly. However, voltage of the capacitor can change like this or can be a steady when dV by dt becomes 0. The further relation we see here that I equals to C dV by dt. So, the I on y axis and dV by dt on x axis, this shows that the corresponding characteristic of the capacitor becomes a linear relationship and the slope becomes C. So, I equals to C into dV by dt. So, dV by dt on x axis, I on y axis, then the characteristic of the capacitor becomes a linear one and its slope becomes C. So, these are the characteristics of the capacitor. Furthermore, from this relation we can have that that the voltage must vary with time for a current through the capacitor. If current is non-zero, then the corresponding voltage across the capacitor must change with time. Capacitor is open circuit condition for a DC voltage at steady state. When it is steady state, it means that the corresponding dV by dt becomes 0, then current becomes equals to 0. So, that leads that the corresponding current becomes 0. So, in steady state the DC voltage dV by dt becomes 0. So, that means that the corresponding current becomes 0, which condition is called this open circuit condition. So, that is the second point for the capacitor, implies capacitor is open circuit condition to DC voltage, DC means fixed voltage across the capacitor and that at steady state. Capacitor voltage cannot change abruptly, which we have already discussed in terms of that. So, these are the three important properties of the capacitor from the voltage and from the current voltage relationship I equals to C dV by upon dt. Now, from the same relation I equals to C dV by dt, we find the V from the current. So, we can write the corresponding equation, integral equation 1 upon C minus infinity to t I tau into d tau. So, that becomes equals to V t equals to 1 by C t 0 to t I tau d tau plus b t naught, where b t naught is q t naught by C, q t naught the initial charge, the voltage across the capacitor at time t 0, initial charge upon C. So, if you have a initial voltage here in the capacitor, using that we can find the corresponding capacitor voltage at any time t from this relation V t equals to 1 upon C t 0 to t I d tau plus B t naught. So, that is the from this relation we can find the corresponding capacitor voltage at any instant of time in the circuit for the given circuit condition. Moving forward, from the basic relation I equals to C dV by dt, now we can say that the corresponding voltage across the capacitor is V with plus sign this side, minus sign this side and current entering I. So, therefore, if we remember the corresponding resistance like case a load kind of thing at any instant of time, then the instantaneous power delivered to the capacitor what the capacitor takes, that becomes equals to from this circuit condition P into V I, P into V I at positive terminal of the capacitor current is entering. So, we call it a power delivered to the capacitor, power taken by the capacitor. So, that becomes equals to from the relation C V into d V upon dt, C V into d V upon dt. So, therefore, this is power. So, energy P into T. So, energy stored in the capacitor E, that becomes equals to minus infinity to T P tau d tau, energy stored in the capacitor in a time period up to T. So, that becomes equals to, if we substitute the value of P equals to C V dV upon dt. So, C minus infinity to T V dV upon d tau d tau. So, that is becomes equals to C V infinity V t integral of V infinity to V t V dV. So, that becomes equals to integral of V dV gives us half C V square. So, V infinity to V minus infinity to V t. Assuming the capacitor was uncharged at t infinity. So, V infinity equals to 0, V minus infinity equals to 0, capacitor was not charged having V equals to 0 at minus infinity. Then this corresponding energy relation E equals to half C V square, this part becomes 0, that becomes half C V square, or if we substitute in terms of the corresponding C V equals to Q, then we got E equals to Q square upon 2 C, or as a very common formula E equals to half C V square, given that the corresponding voltage in the capacitor V minus infinity equals to 0. So, this is about the energy stored in a capacitor at any instant of time t when the corresponding voltage across it is V. Now, we will find through an example and try to understand the energy concept. From that relation what we have studied about the property of the capacitor, that capacitor becomes an open circuit in DC at steady state, and the energy stored is half C V square. Find the energy stored in the two capacitors, 2 microfarad at 2 millifarad and 4 millifarad at steady state if the circuit draws 6 milliampere DC from the source at an instant of time. So, the circuit has certain resistances, and across different resistances capacitors are connected, like at across 2 kilo ohm resistance 2 millifarad is connected, and in the path 5 kilo ohm and the 4 millifarad are connected in series. So, the question asks is that what is the corresponding energy stored in this 2 millifarad and the corresponding 4 millifarad capacitor. So, as you know, this is a DC circuit. So, therefore, that concept we have already learned, that I equals to C dV by dt, that reveals that the capacitor at steady state behaves like an open circuit, current through the capacitor becomes 0. So, no current flows through this capacitor. So, this becomes I equals to 0, and no current flows through this capacitor, I equals to 0. So, that leads to a situation that the corresponding circuit becomes like this. So, we have 2 kilo ohm and we have 4 kilo ohm, and we have here 3 kilo ohm. This is connected like this, and here the corresponding circuit becomes here, this becomes the open circuit condition, and here the circuit here also becomes open circuit condition. So, the capacitor becomes open circuit condition at the two capacitors. So, that implies that the corresponding current here 6 milliampere now will flow through this path and also through this path. So, this 2 parallel plus 3 in parallel with 3 kilo ohm in parallel with 2 kilo ohm plus 4 kilo ohm. So, these are the 2 parallel paths. Now, across the 2 kilo ohm whatever voltage is there, let us say this is V 1. So, this V 1 is nothing but across the capacitor 2 millifarad. So, how much is this V 1 in this case, say V 1, that is V 1 across 2 kilo ohm. So, that becomes equals to the current through this path into the corresponding resistance. So, current through this path is parallel combination. So, 6 milliampere into 3 upon 3 plus 2 plus 4. So, that is the corresponding current through this branch into the corresponding this current, this is the corresponding current through this band into the corresponding 2 kilo ohm voltage across the 2 kilo ohm. Similarly, corresponding voltage across this capacitor will be nothing but voltage across the 4 kilo ohm. So, get the corresponding voltage and then the corresponding half CV square formula gives us the corresponding energy in each capacitor. So, going to the solution, as I said, for this circuit becomes in a DC environment becomes open at the 2 capacitor position. So, this is about this. So, let us say this is V1 and this is V2 voltage and the current flows one path is like this and one path becomes like this. So, let us the corresponding current to this 2 kilo ohm 4 kilo ohm in series is current I. So, we will find the corresponding I. So, the I becomes equals to 3 upon 3 plus 2 plus 4 into 6. So, this is happens to be 2 milliampere. So, this corresponding I happens to be 2 milliampere. So, voltage across the 2 millifarad capacitor becomes the corresponding 2 milliampere into 2 into 2 is 4 kilo ohm, 2 milliampere into 2 kilo ohm. So, that gives us 4 volt. So, this is nothing but V1. Similarly, the V2 becomes equals to 4 kilo ohm into the corresponding current is 2 milliampere. So, that gives us 8 volt. So, this is 8 volt, this corresponding V2 becomes 8 volt. So, across this becomes the corresponding 4 millifarad capacitor is 8 volt and across this is 4 volt. So, therefore, this E1 energy stored in the 2 millifarad capacitor becomes half C1 V1 square and that becomes equals to 16 millijoule, and E2 the energy stored in the second capacitor 4 millifarad capacitor is having half CV square. So, that becomes equals to 128 millijoule. So, that is the energy stored in such a circuit arrangement with such a circuit condition also. Parallel connection of capacitors. So, C1, C2 and C3 and like so, let us say are connected in this fashion. So, all are parallel. So, the voltage across the corresponding capacitor will be same. Now, let us say at an instant of time the corresponding combination takes a current of I from the source and each capacitor is drawing a current I1, I2, I3 and the corresponding charge associated with them will be Q1 equals to C1 into V, Q2 equals to Ct into V, Q3 equals to Ct into V. And let the corresponding equivalent that becomes equals to C equivalent with V, and as already earlier mentioned, equivalence means the current at this terminal from the source side and the voltage that must be same. So, we have to talk about same V and the corresponding current from this source side becomes I. So, terminal current and the voltage remain same. So, with that say we say that the corresponding current at this KCL if we apply, then I becomes equals to I1 plus I2 plus I3, but I1 equals to we know that equals to C dV by dt. So, C1 dV by dt, C2 dV by dt, C3 dV by dt, I1, I2, I3 respectively. So, that if we compare to this one, this side from this circuit, we say that I equals to C equivalent dV by dt. So, we say that dV by dt is common. So, I this side, so this is I. So, that means that this I the C equivalent becomes equals to C1 plus C2 plus C3. I and dV by dt remaining same for the equivalent circuit. We say that the corresponding dV by dt here common. So, C1 plus C2 plus C3 is the corresponding C equivalent. That implies that in the parallel combination the corresponding capacitances are added. This is unlike that of resistance. In resistance we have series combination R1, R2 and R3 are added. In the lab we will see also the parallel combination of the capacitors. So, C1 and C2 are in parallel. So, the corresponding C equivalent becomes equals to C1 plus C2, that you know from the theory. Now, C1 plus C2 means the corresponding C value now increases. So, therefore, the Xc value will decrease, it means that the corresponding Is value will increase. So, that also we can notice from the observation in the lab. So, the objective here is to find the equivalent capacitance of parallel capacitors, that will be equals to C 1 plus C 2. We have capacitors connections. For that, the corresponding setup is ready here. First, we will see if the two capacitors are connected in parallel, what will be the corresponding the combination capacitance. For that, we will have the multimeter, the corresponding value here. So, this one capacitor which shows very close to the 10 microfarad one, 9.97 or so, and then we will connect to another such capacitor having 10 microfarad. These are connected in parallel. So, this parallel combination now, the corresponding capacitance value from the meter happens to be 19.99 microfarad. So, what you see that with parallel combination of the capacitors C1 and C2 as marked here, 10 microfarad, 10 microfarad very close to that, the corresponding capacitance is increased, and that happens to be C1 plus C2, 19.99 microfarad. Verify that capacitance series parallel combination they will change. Then for that case, we have this supply system now, and we will see how the corresponding capacitance parallel combination of the capacitance value, the capacitance effective capacitance increases. So, we have a 10 volt supply here, 10 volt peak to peak supply here. So, this is 50 hertz. So, this AC supply now given input to this one capacitor 10 microfarad mil, and in this case the corresponding current drawn by this capacitor is having 0.022 ampere. So, this is the corresponding current drawn by the capacitance, because it has a reactance 1 by C omega reactance value. Now, what will do that in parallel with this we will have another capacitance connection same value 10 microfarad, and we see the corresponding current now. The current now increases to 0.042. So, the current increases because the effective reactance decreases, and this is from there we can conclude that the corresponding capacitance value increases 1 by C omega equals to x, because x reduces, so therefore this increases. So, this is clearly we can clearly from this state that with the parallel capacitance the corresponding capacitance value increases. So, now we will take from the observations from the lab what we took, that omega is here is 314.16 radian per second for the 50 hertz supply, Vs is 7.07 volt, that is maintained. So, once we supply to the only one capacitor C1, then the corresponding current drawn is 0.022 ampere, that we have already seen. Corresponding C1 is 9.97 microfarad, and that the corresponding calculated one happens to be also IS happens to be based using the corresponding X and the corresponding XC and the corresponding Vs, we got it to be 0.022 ampere. So, that is verified. Now, connecting the corresponding capacitors in parallel, the corresponding current is now increased from 0.022 to 0.042 ampere, and the calculated value of the C1 and C2, the C equivalent we got it from 19.99 from the multimeter microfarad, and using that calculated one we got the corresponding current to be 0.044 ampere. So, that we see that if the C1 and C2 value they happen to be same, then the corresponding C equivalent happens to be the 2C in that case, and thereby the corresponding Xc happens to be half of the corresponding, this X equivalent C happens to be half of the corresponding that of the X for the C1 case. So, we see that current increases here when the corresponding combination happens to be parallel. Now, I will go to the series combination of capacitors. Let us the C1, C2, C3 are connected in series, and then we have a applied voltage at an instant of time in the circuit becomes V across the 3. Then a current is flowing through these capacitors series path, same current. So, corresponding charge will be also same in C1, C2, C3. So, charge in C1 is Q1. So, C1 into V1 is Q1, C2 into V2 is Q2, and C3 into V3 is Q3, and all are same. Now, let us say we are talking about the equivalent of these two. So, as I mentioned earlier, the equivalent implies that the corresponding terminal current and the voltage will be same. So, same voltage and the corresponding terminal current is I, and the equivalent capacitance is C equivalent. that results in at any instant if the corresponding current run is I and we apply the KVL through this loop, we apply KVL through this loop. So, that results in V 1 plus V 2 plus V 3 equals to V applied voltage, rather we say that the corresponding this is V supplied voltage. So, this V minus plus plus minus plus minus plus minus. So, that if we see, so that becomes equals to V minus V 1 minus V 2 minus V 3 equals to 0, that is about the KVL in through the loop. So, that results in V equals to V 1 plus V 2 plus V 3. And if we substitute this V 1, that equals to Q upon C 1, because Q is C 1 V 1 and the Q are same, because I is same throughout, I into T gives us Q. So, therefore, from these two relations for this equivalent capacitor in equivalent for these two circuits shown, then we say that 1 upon C 1 plus 1 upon C 2 plus 1 upon C 3 is nothing but 1 upon C equivalent. So, this is similar to that resistance in parallel, similar to the condition resistance in parallel. So, we saw that in series combinations the corresponding capacitance decreases, but in parallel combination this combined capacitance becomes C 1 plus C 2 plus C 3 increases. So, the capacity increases, it means that the storing charge capability also increases in terms of that aspect. Now, in the laboratory we will see how the series combination results in the corresponding C equivalent. So, theoretically we know that when C 1 and C 2 will be connected in series like this, then the corresponding equivalent C equivalent will be C 1 C 2 upon C 1 plus C 2. So, we see that the series combination results in smaller C, lesser value of C, and therefore, the corresponding one C reduces in a AC environment connected like this, then the corresponding XC will be higher. Once XC is higher, then the corresponding IS will be reduced as compared to the, let us say, only C 1 and only C 1 or C 2 are connected. So, if C 1 and C 2 are of same value, then the this C equivalent results in to be C by 2, C 1 by 2, when C 1 and C 1 equals to C 2 and so. So, that way I can say that, and then the corresponding current will also will be the corresponding current will be reduced by half. So, IS in second with series combination case will be only C 1 divided by 2. So, that we like to observe. So, the objective here is to verify that the corresponding series connections the equivalent happens to be C 1 C 2 upon C 1 plus C 2. Now, with the series connection of these two capacitors C 1 and C 2 both having very close to 10 microfarad, we see that in the meter it is showing very close to 5 microfarad, that is 4.997 microfarad. So, you see that in case of series combination of C 1 and C 2 each are having 10 microfarad, then the corresponding combination happens to that the capacitance value decreases by factor. So, this is C 1 and C 2 both having 10 microfarad. This happens to be C 1 by 2, that is 5 microfarad. So, the value comes up to 4.97, very close to 5 microfarad. We have the series connection of the capacitor. So, these two C 1 and C 2 capacitors of 10 microfarad are connected in series. From the same 10 volt peak to peak AC 50 hertz supply, the corresponding current drawn is clearly showing 0.010 ampere, 0.011 ampere and so. So, this clearly shows that the corresponding current is small, it implies the reactance becomes higher, and the reactance becomes higher means capacitance becomes smaller. So, this C 1 and C 2 in series results in the corresponding capacitance value to be smaller in that aspect, C 1 by 2 percent. So, this is clearly understood. From the observation on the series connection of C 1 and C 2, so we will try to check. Now, let us say only C 1 or C 2 is available. So, in that case the corresponding measurement now this becomes equals to that each C 1 is 9.97 from the multimeter we see, and at that time the corresponding current supplied from the source with a 7.07 volt supply, that happens to be 0.022 ampere. Now, omega, this is a 50 hertz supply system. So, the omega happens to be 314.16 radian per second. substituting the value of the C and the omega, we got the Xc value and then the Vs is 7.07. So, we calculate the corresponding Is from the Xc value and it comes out to be 0.022 ampere. This is same as the corresponding measured current here through the ammeter and the oscilloscope. So, that is the point. So, that we say that the corresponding C value gives only one value of C gives us 0.022 ampere. So, simple calculation also that reveals in terms of that. Now, C1 and C2 both connected in series where C1 and C2 are of same value. So, the corresponding multimeter gives us 4.97 microfarad and the measurement of Is gives us 0.011 ampere. So, what we see here that 0.22 ampere earlier for only one C1, C1 and C2 the corresponding current is reduced, it means that the corresponding X equivalent is increased and that means that the C value, the C equivalent is decreased. So, that is the straightforward comparison and it is factor of by 2. So, that is why the corresponding here the corresponding current reduces by factor of 2. So, we say that the Is also we calculated in terms of the substituting the value and that comes out to be also 0.011 ampere also. So, the thing we notice here that with C1 equals to C2 the corresponding C equivalent happens to be C1 by 2 and that is noticed from the corresponding straightforward observed from the corresponding current reduction by factor of 2. So, find the equivalent capacitance seen at the terminals A and B of the circuit shown here. So, we like to find the CAB or C equivalent at the terminal AB. So, what we see here that 60 is in parallel with 80. So, the corresponding point here to here will be 60 plus 80 microfarad. This will be parallel means added. Then these combinations now 60 plus 120, 60 and 120 are in series. So, then this will becomes equals to 60 into 120 divided by 60 plus 120. So, this is in microfarad, this combination, this and this. So, this is in parallel with this. So, this plus 620, so that becomes this and this becomes in series with this. So, this let us say this is x 1 and this is x 2. So, then this becomes in parallel, this becomes in series means x 1 into x 2 divided by x 1 plus x 2 and that will be nothing but your C equivalent. So, that way if we go by that then we see that as I said 60 and 80 are in parallel. So, 60 plus 80 is 140 microfarad. Then this 60 and 120 are in series. So, that gives us 40 microfarad. So, this combination is 40 and 20 are in parallel. So, therefore, 40 and 20 it means that 60 microfarad. So, this 60 microfarad is in parallel with the first one 140 microfarad and therefore, the C equivalent becomes is series with this 40 and the corresponding 140 are in parallel 60 and the 140 are in parallel. So, that gives us 60 into 140 upon 60 plus 140 the resultant becomes 42 microfarad. So, this C equivalent becomes commonly 42 microfarad. So, we should note that this is the other way that of resistance combination, series and parallel combination. And the voltage across capacitor in series connection, let us say C1 and C2 are two capacitors. So, we have already seen about the series combinations. So, that series combination C equivalent becomes equals to C1 into C2 upon C1 plus C2. So, this V1 and this V2. So, at any instant of time V equals to V1 plus V2 across the corresponding combinations. So, this Q equals to nothing but same current flowing is I is same. So, that means that charge in each capacitor plate becomes same. So, Q equals to C1 V1 equals to C2 V2. So, from this relation V1 upon V2 equals to C2 upon C1 and if we add 1 to both sides then this becomes equals to V1 plus V2 upon V2 equals to C2 plus C1 upon C1 and V1 plus V2 is nothing but V. So, we got the relations to be V upon V2 equals to C2 plus C1 upon C1. So, this results in V2 equals to V into C1 C 2 plus C 1, and that therefore, and the similar to that V 2 V 1 becomes equals to, where V 1 is nothing but V minus V 2, that becomes equals to V into C 2 upon C 1 plus C 2. So, what we see here, that the relation that this V 2 relation and the V 1 relation, V 2 equals to V into C 1 upon C 2 plus C 1, V 2 equals to V into C 1 upon C 1 plus C 2. So, voltage of V 2 depends upon the C 1 and voltage of V 1 depends upon the C 2 upon C 1 plus C 2. So, the voltage division becomes like this. So, this is not the same way as we have seen for the resistance. So, for example, find the voltage across each capacitor in the circuit in steady state. 10 microfarad and 5 microfarad are connected in series, and we have at an instant of time the voltage across the corresponding combination is 150 volt. So, it means that V 1 plus V 2 will be 150 volt, and as already said, the V 2, the voltage across this one will be 150 volt into C 1 10 upon the C 1 plus C 2. So, that gives us 100 volt across the 5 microfarad capacitor, and V 1 becomes equals to 150 the combined voltage into the corresponding C 2 upon C 1 plus C 2. So, that gives us 50 volt. So, what we see that the V 2 becomes equals to 100 volt and this becomes equals to 50 volt. So, we see that higher capacitor, higher value of capacitor has lower voltage and smaller value of capacitor has higher voltage, and 100 plus 50 becomes combination of 150. So, that is the point, and this is coming from the, because series current is same, charge is same. So, Q equals to C V, then Q remaining same. If you have a higher C, then the corresponding voltage becomes smaller, because C V product becomes same in this case. So, this is the from the basic property of the capacitor, we talk about the voltage distribution in a series combination case. Now, we will see what happens to the star delta and delta star transformation for the capacitor combinations. So, let us say first in the case of delta to star transformation. So, delta things are available, we have delta things are available, like here terminals 1, 2, 3, Z 1 2, Z 1 3 and Z 2 3, similar to we have used in case of resistance and impedance combination in AC. So, these three are available, and we like to find the corresponding star, the Z 1, Z 2 and Z 3 as the equivalent. So, we know from this delta star combination for the impedances, because impedances that happens to be similar to the from the equivalence terminal equivalence perspective, the resistance also. In the equivalence, we say that if you apply voltage between 1 and 2, then the current through this flowing through will be same whether you have star or whether you have delta. With that equivalence terminology, earlier we have mentioned that the Z 1 for the star, that becomes equals to Z 1 2 into Z 1 3 upon Z 1 2 plus Z 1 3 plus Z 2 3. So, if we remember, then the star equivalent, the Z 1 at this terminal 1, this terminal 1. So, the combination, the product of Z 1 2 and Z 1 3, Z 1 2 and Z 1 3 upon the sum of the delta resistances, delta impedances. So, that is the corresponding relation. So, now suppose we to this impedance we consider in AC environment kind of thing, and omega equals to 1 radian per second for easy calculation of equivalence, omega equals to 1 radian per second. So, Z becomes equals to minus of j x c for capacitance, x c is 1 by omega c. So, this becomes equals to 1 by j omega c, and that becomes equals to omega being 1, we can consider it 1 by j c. So, substituting this 1 by j c terminology perspective for different impedances. So, for Z 1 I substituted this the 1 by j c 1 capacitance C 1, they are corresponding because all are capacitance now these impedances. capacitive reactance we can consider now. So, Z 1 substituted by 1 by J C 1 and similarly Z 1 2 by C 1 2 and Z 1 3 by J C 1 3 and then Z 1 2 J C 1 2 and this Z 1 3 by J C 1 3 and this Z 2 3 by J C 2 3. Then we find that the corresponding C 1 1 by J C 1. So, all J left and right will cancel. So, we see that the corresponding C 1 becomes equals to 1 by C 1 plus 1 by C 1 3 plus 1 by C 2 3 upon 1 by C 1 2 into 1 by C 1 3 from these steps. So, this relates to be the corresponding this to be like this, and from this if you see this C 1 2 C 1 3 here will cancel out, C 1 2 and C 1 3 will cancel out. So, only C 2 3 remains. So, therefore, this becomes equals to C 1 2 C 1 3 C 1 2 C 1 3 and then the C 1 2 C 1 3 upon C 2 3. So, we see that we are going for delta to star transformation, delta things are available and from here we are getting the star, and the relation here is we see here the star value C 1 that happens to be C 1 2 plus C 1 3 C 1 2 C 1 3 upon C 2 3. Now, similarly, if you go by this the corresponding formula here, then we will get the corresponding C 2 to be equals to C 1 2 C 2 3 plus C 1 2 C 2 3 upon C 1 3, and for C 3 this becomes equals to C 1 3 C 2 3 plus C 2 3 plus C 1 3 C 2 3 upon C 1 2. So, what we see here is that the corresponding relation here, unlike that of the resistance and impedance, we got the corresponding relations to be for star case, we got the summation of the corresponding capacitance connected to C 1 2 and C 1 3, and then we got the corresponding relation for C 1 2 plus C 1 3 upon C 1 2 C 1 3 C 2 3. So, what we see here that the corresponding C 1 in star happens to C 1 2 C 1 3, the corresponding C 1 2 C 1 3 this C 1 value into plus the C 1 2 C 1 3 upon the third one C 2 3. This is similar to the transformations we see carried out from the delta to not delta to star, star to delta. So, that is the difference between star delta transformation of impedance, resistance, and now we are discussing about capacitance. Now, in a similar way we can go for the star delta transformation, star things available and we are getting delta. So, from the impedance relations which we have already discussed in AC and similar to that one. So, we know that Z 1 2 the delta 1 will be equals to Z 1 plus Z 2 Z 1 plus Z 2 Z 1 into Z 2 upon Z 3. Now, in a similar fashions with omega equals to 1 radian per second, if we substitute and substitute the corresponding capacitance value here, because this is only capacitive circuit. So, then I substitute this Z 1 2 by equals to 1 by J C 1 2 and Z 1 and Z 2 respectively 1 by J C 1 and plus 1 by J C 2 and like this. Then I get the corresponding C 1 2 for the delta to be equals to C 1 C 2 upon C 1 plus C 2 plus C 3. What this reveals? This reveals that delta circuit C 1 2 is C 1 into C 2 star C 1 into C 2 upon some of the resistances of the star. So, this similar to the we move from, we can say that not star to delta, delta to star, you can say that transformation we carried out in case of resistance or impedance. Similarly, for C 1 3 also C 1 C 3 upon C 1 plus C 2 plus C 3, and for C 2 3 also C 2 C 3 upon C 1 plus C 2 plus C 3. So, this is what the corresponding relation. So, this star delta and delta star relation comes out to be just the other way what we find for the resistances or impedances. So, let us have an example. So, we have a circuit like this with between terminal A and B we have a capacitor combinations of like this. So, 25 microfarad, 10 microfarad, 15 microfarad and 20 microfarad with C and D terminal having 10 microfarad. So, the question is there, find the terminals capacitance between terminal A and B. So, if you see this circuit, then we need it is neither series or parallel combinations. So, it contains we require a delta star or star delta transformation as we have already practiced for resistance and the impedance circuits. So, we can do different ways, we can go for the star transformations, star delta transformation at C, star delta transformation at D, or you can change any delta combinations to a star combinations and you can simplify the circuit. Let us here we can change the corresponding star combinations 10 microfarad, 15 microfarad and 10 microfarad to a delta combination. In these delta combinations, as you see here, so the D node will be removed and we can have the corresponding combinations like capacitor here for these 3 capacitors and another capacitor between A to B. So, finally, the corresponding circuit becomes like this, that we have A terminal and we have B terminal and we have C terminal here and no more D terminal. So, if you see this, then from this A terminal we have already a capacitor of 25 microfarad that will remain untouched and we have C to B terminal which will be having a capacitance of 20 microfarad that will be untouched, but we will now remove the 10 microfarad, 15 microfarad and 10 microfarad connected to D. So, in place of this we will have 3 combinations. So, let us say we can say that from A to C another capacitance. So, let us say this is our C1 here and now let us say we have C to B another capacitance will come for the from this transformation. Let us say this is C2 and then we have another one from A to B, this is C3. So, let us say this is C3 will come from A to B. So, what we see here that after this transformation of the delta to star to delta, we can get the combinations like this and let us see whether the corresponding circuit is simplified or not. You see here for from A to C this is a parallel combinations, from C to B this is a parallel combinations. So, this is parallel means added and then we have a series combinations. So, that we can simplify this path and then this path is A to this path is in parallel with the C3. So, therefore, it means that the corresponding CAB can be obtained from the simplified network. So, by this way if you go for the calculations now, so as I said here, so these combinations becomes, so the D is now removed and then we are getting two impedances like 25 microfarad with C1, 20 microfarad with C2 and the corresponding C3 and then you can find the corresponding things. Now, you see here at the C point this becomes parallel. So, we can get the combinations to be C4 and we can get the combinations to be C5 and then in C3 in parallel and then you can find out the corresponding CAB. So, what we say that this replacement, so C1, the C1 will be now between A and C. So, between A and C, so C1 means this will be 10 and this will be 10 and 10. So, 10 into 10 into 10 because you are going for the corresponding star to delta. So, 10 into 10 divided by the sum of the star resistances. So, that becomes equals to 20/7. C2 now becomes equals to between C and B. So, that becomes equal to 10 into 15 divided by the sum of the star. So, that becomes equals to 30/7. C3 is between A and B. So, this is associated with the 10 and 15. So, 10 into 15 divided by the sum of the star resistances, that gives us 30/7. So, we got the corresponding C1, C2, C3, substitute in this circuit and then we can find the corresponding combinations. So, C4 becomes equals to parallel of this. So, that is why 25 plus 20/7, C5 is parallel of 20 and the corresponding C2. So, that becomes equals to 20 plus 30/7 and then we have C3. So, the combination gives us the CAB becomes equals to 17.26 microfarad. So, what we say in this lecture in that we discussed about the basic properties of capacitor, then we went for the series and parallel combination of capacitor, also the voltage division across capacitors in a series combination, and then we talk about delta star and star delta transformation, and we found the corresponding relations to be different than what we have learned for simple resistive circuit in a DC environment. Thank you.